Matthew. And then I'm looking anybody yet. Hello. Over on our little back computer, if you got the grade 12 periodic table last day and you would like to trade it in, you can take one of those and give me the other one. There's also the, what's the other thing I'm looking for? The acids and hydrates is over there. So if you're interested in grabbing that, that is also over there. Yes. Yeah. Oh, I should tell everybody this. Thank you very much. Okay, my friends. So sometimes after school I go home, and yesterday I had someone who was taking chemistry online, chemistry 12 online, and he came and asked me questions for like 45 minutes. So don't take your courses online, take them in the school so you can ask your teacher. So that's why I got home and I was like, I don't even know what happened, and I did not put up the lesson, and I didn't put up the notes until this morning at like some ridiculously early time. So if you were looking for the class notes, over in the channels are class notes. I'm hoping it's there. Let's see. Yes. Sometimes if this doesn't show up for you, it just means you need to wait for Teams to think about it. You know, you need to go there and let it process a little bit because it needs to think of things. I don't know. Teams seems to be that way. So Microsoft, I don't know. So there that is. And I am trying to remember, I'm recording our lesson, huzzah. Okay, so now we have a lesson that has been recorded. Did you have any questions from anything that you did last day for homework? Yes. Yes. Why is it an important number? That's actually a really, really good point, and Tyler is going to talk to you about that tonight. But I will start by saying it's a really important number because if I want to know the amount of carbon that is in this pencil lead, because a pencil is, the pencil lead is completely carbon, I can't go along and count the atoms. 1, 2, 7 billion, 7 billion, 1, 7, you know what I mean? Like that's not going to work. So a mole is the quantity. Now, do you guys know the mass of a carbon atom? Like if you go look on your periodic table, yeah, it's 12.0 AMU. Yes? Okay. Well, if you have a mole of carbon, if you have 6.02 times 10 to the 23 carbon atoms, that's going to equal 1 gram of carbon. Or sorry, 12 grams. 12 grams. Right? So 1 mole of carbon is 6.02 times 10 to the 23 carbon atoms is 12 grams of carbon. So if I want to know how many carbon atoms I have, I can weigh it and then use a conversion factor to figure out how many particles that is. Because it's not, I'm not going to be able to actually count them, but I can easily weigh it. Yes? How did they determine that? That's a good question, and I'm going to think about that. Okay, I think I know, but like right now it's not coming to my brain because end of the day, like I'm always a little bit like, so yeah, I'll think about that as we go. How did we come up with that number? How come up with, okay. I think it had things to do with gases and ratios and things like that, but yeah. So if you have 1 atom of carbon, the mass is 12 AMU, yes? If you have 1 mole of carbon atoms, the mass is 12 grams. That's why they picked this number, because it's the number that scales up from 1 particle to 1 mole to it, from AMUs to grams nicely, okay? So if you had, what is the mass of 1 atom of helium? 4. 4 AMU. What does AMU stand for? Atomic mass units. Okay, what is the mass of 1 mole of helium? 4 grams. Okay, and it just so turns out that 6.02 times 10 to the 23 is the number that allows us to measure in grams nicely. Okay, we could have chosen something different, but then the 12 wouldn't scale up to 12 nicely. It wouldn't be pretty, yes? It is not an exact number. It is actually, let's go see, there might be an exact version of it. Yeah, Ms. Wu actually has it on her. She's like done this nice thing. She's got little cutouts of the numbers, and I'm like not that clever. Oh, this is not the kind of mole digits I want. Okay. No. Okay. Chemistry. Okay, there we go. Okay, 6.0, in fact, 6.02 times 10 to the 23 is what you will learn in grade 11 because it is too much trouble for me to teach it one way to the regular grade 11s and one way to you guys because all my resources, I would have to change every answer key and have different significant figures, and it would drive me crazy. But on the AP exam, the version of the mole, they actually give you the number in their data table, okay, and is actually, they use 6.022 times 10 to the 23, but the number is actually, oh, let's see, here we go, Wikipedia, 6.02214076 times 10 to the 23 elementary units. So that is the exact number, yes? But when you say 6.02, you are only using 3 of those digits, and so that has 3 sig figs. Yes? If you want to calculate it using 6.02214076, and you're going to write that down so that whoever's marking it knows that you have used that unit, then God bless you, keep on going, okay? But yeah, I would prefer it for my answer key's sake if you use 6.02, all right? And then when you write the AP exam, just add one more digit, 6.022, okay? So yeah. All right, so yeah, the 6.02 has 3 significant figures. All right, anything else that you were puzzled about by the homework or anything like that? So we're good. All right, and how did the converting go with Tyler? That was okay? Yes, very good, very good, very good, very good. Did I ask you to do 5.1c? No, I don't think so. Also, the answer key says 20. Oh, it's different in here. Oh. You're right. Okay, I thought it was the answer key. Answer key. It's right in here. Okay, so that's page 12. Page 12. Yep. Yep. So just a quick preview. 5.1c on page 12. The answer for 2D should be 20 with a dot, not 19.9. Okay? You were not required to have done that, but I had, people were working ahead and whatever, so that's great. Not 19.9, but 20.0. Is there another way you could write this to let me know that it has 2 sig figs? You could write it as 2.0 times 10 to the 1. How do we feel about scientific notation? Let's do a thumbs up, thumbs down, thumbs in the middle. Thumbs up and thumbs in the middle. Okay. What I might do is I might have a little review lesson on that next day, okay? Or something along those lines. There is one final way you can do it. This is not generally very standard, but if you do it for me, I will be okay. But if you go to university, ask your professor what they like. You could also write it like this. And that shows you that that is the uncertain digit. This over bar indicates the final uncertain digit when it is a 0. But you know what? Yeah, that could look like a repeater. So I tend to like these better, okay? So if the overbar confuses you, you can just pretend you never saw it, okay? But if you like it, you may use it, okay? All right. So we are going to now go to page 14, 5.1e. What kind of a particle do we see at the top of page 14? That is carbon dioxide. How do you know that it is carbon dioxide? It's got one carbon and two oxygens, dioxide. Excellent. And what type of particle is that? What general category of particle does that entire thing belong to? It is a covalently bonded substance, which means it is a molecule, okay? So these here, these are covalent bonds. And the entire thing together is a molecule. And how do you know that it's going to be a molecule and have covalent bonds? Yes? Yeah, they're all nonmetals, okay? That means we're going to have covalent bonds between them. What does it mean to have a covalent bond? Yeah, the electrons are shared. Okay, so here we have our molecule. It is made of one carbon and two oxygens. How many oxygen atoms are in one molecule of CO2? There are two. So you could write that as a conversion factor, a one thing over the other thing, yes? So you could say I have two oxygen atoms for every one CO2 molecule. MC stands for molecule because molecule is really long to write and you cannot abbreviate it mole because a mole is something different. Yes? So capital M, capital C is how I abbreviate molecule. I don't think that is standard. You know, again, if you go to university, ask your professor how some people write molec, but I'm like, MC is shorter than molec. I like that better. Okay. Oh, we've already written it as a conversion factor. I'm getting ahead of myself here. I am very, very sorry. So this is 2 O atoms for every one CO2 molecule. Here, get rid of that there. 2 O atoms for every one CO2 molecule. If we have 3 molecules of CO2, how many oxygen atoms do we have? We have 6. 1, 2, 3, 4, 5, 6. I tend to write a big space in between my 6 and my 0, my 6 and my O, because otherwise it looks like 60. And I write a big space in between the O and the atoms because otherwise it looks like otoms, which sounds like a fun kind of breakfast cereal, but you know, maybe not for chemistry. How would we calculate this using conversion factors? So when we're using conversion factors, we always have our unknown, which is equal to some initial quantity. Are you familiar with the UI? Or no? Okay, U stands for unknown. The I stands for the initial quantity times a conversion factor. This is dimensional analysis, okay, which you learned over the summer. And we're going to be reviewing right now. And if you remember, a conversion factor is always in what format? It's got one thing over top of a second thing, yes? So the conversion factor is always in this format, A over B, okay? And this will be unit 1, and this will be unit 2. These two things must be equal. So if I was to put things in there, I might have 100 centimeters on the top, and I might have, what could I put on the bottom? I could have 1 meter because those two things are equal, okay? So these two things must be equal. So if you know two things are equal, you can use them as a conversion factor. So in our question, we are starting with 3 molecules of CO2. That right there is our initial quantity. That's our initial value. So we can write that down here. We can say my unknown is equal to my initial quantity, 3 molecules of CO2, times, so we've had our unknown, we've written down our initial quantity, and now we need to write down that conversion factor, and it's always going to look like this. Okay, and I almost always write in the line first and then start writing in my units because it's helpful that way. What's going to go on the bottom of that conversion factor? Molecules of CO2, because the whole point is to do that. If you have something on the top and something on the bottom, what do they do to one another? They cancel out. So I need to have my molecules of CO2 on the bottom, and what's going to go on the top? That's going to be my oxygen atoms, because I want to find oxygen atoms, and now I have oxygen atoms. So my units are all there, and now all I have to do is put the numbers into that conversion factor. And we know that there are 2 O atoms for every 1 molecule. And I'm going to make that O a little bit further over so it doesn't look like 20. 2 O atoms. And we get as our final answer 3 times 2 is, guess what? 6 O atoms, exactly how many we counted. Okay, which is lovely, and you're like, why would I bother with that? Except that you're not going to be working with 3 carbon dioxide molecules, you're going to be working eventually with, 3 moles of carbon dioxide molecules, and then you'll have to figure out how many particles that is, and then you'll have to figure out how many oxygen atoms are in that many carbon dioxide molecules. Okay, that's where we're going with this. So, how many CO2 molecules can we make with 8 oxygen atoms? So here's my 8 oxygen atoms, 1, 2, 3, 4, 5, 6, 7, 8. One, two, three, whoops, 4, right? You can count it. Yes, you can be like, okay, excellent. I can count that, I can make 4. How would you show that using conversion factors? We're going to start by writing down our unknown quantity. What is our unknown quantity in this question? Yeah, how many CO2 molecules? What is our initial quantity in this question? The number of oxygen atoms, that's the initial quantity given to us, so that's 8 O atoms. And our conversion factor, you can write it either there are 2 O atoms per 1 CO2 molecule. Is there another way we could write that conversion factor? Yeah, you can just flip it upside down. Okay, so or, and you don't have to write all of this out every time. I'm just, reviewing some of what you did during the summer. Okay, or 1 CO2 molecule for 2 O atoms. And then you just pick which one makes your units cancel out properly. Yes? So we're going to have our unknown is equal to our initial quantity times the conversion factor. So we don't know how many CO2 molecules we have or can make. That is equal to our initial quantity, our 8 O atoms, times, and our conversion factor, we're going to always draw that line so that we have that there. And are we going to pick version A or version B of our conversion factor? What do you guys like? B? If we do it that way, does it work? Does everything cancel out that we need to cancel out? Yes, it does. Okay, because things on the top cancel with things on the bottom. And now we have 8 times 1 divided by 2 is 4. Yeah, so we have 4 CO2 molecules. And that's going to come in handy when you can't draw 4 little pictures, right? Because you have 800,014 molecules, and nobody wants to draw 800,014 molecules. Either that or you'll need to ask for a time extension. I'll see you in a decade. Bye. Here is methane. For the molecule of methane, I would like you to write conversion factors between molecules of methane and atoms of H, molecules of methane and atoms of C, and then finally, a conversion factor between atoms of C and atoms of H. Check with your partner once you've done that, and then we will go over it together. When you're done, check with your partner, see if you got the same things. Does my conversion factor look like your conversion factor? Yeah, would it be okay to write it upside down? Yes. You know that you can always flip it. So if you're just writing a conversion factor, it doesn't matter which way you write it. You can always flip it if you need to. So you can say, or you could have written 4 H atoms per 1 molecule of CH4. What did I do wrong on that last one? Yeah, that should be 4 H atoms. I don't know why I wrote molecules. While we are here, what type of compound is CH4? It is a covalent compound and it is a hydrocarbon, which means that it is organic. So this is covalent. It is a molecule. It is a hydrocarbon, which means that it is organic. And do you remember what the prefix meth means? 1 carbon. You're like, that means crystal meth, which I know I shouldn't take because otherwise I'll go crazy. Yeah, exactly. So methamphetamine, I assume, is an amphetamine molecule with a methyl group on it. Okay. What is a methyl group? If I have some big complicated structure, you know, I've got carbons bonded to carbons, bonded to carbons, I'm assuming there's some rings involved. There's always some rings involved in the complicated ones. You know, you've got another one over here. Probably not like that, but that's okay. Let's just pretend it's there. Okay. Off of one of these is going to be a C bonded to 3 H's, which is a methyl group. When you have a CH3 sticking off the end of something, that's a methyl group. And that's where methamphetamine comes from. Let's look up what methamphetamine is. Let's look up the structure. I'm sure this is great. This is on my work computer. Okay, here we go. Come on. I want to see the picture. Images. Oh, God, these computers are so slow, it kills me. Images. Come on. So do we see that we have this CH3 group here? Yes, and we have this CH3 group here. Those are the methyl groups that are sticking off of the rest of this structure, and each of these little corners would be a carbon atom with some hydrogen sticking off of it. Okay, so you get these really complicated structures, but sticking off the end, you have those 2 methyl groups, and that's where the meth comes from in that. So our simplest meth compound is methane, which is the simplest hydrocarbon that there is. Okay? While we're at it, why on earth does it look like this funny tripod-like structure? Can you guys imagine that's like a tripod with a little camera sticking up the top? Okay. Why does it look like that rather than just a flat carbon thing like this? Like, why is it not just 2D? Yes. Yeah, so this one is a ball and stick model. It represents the actual structure rather than, do you guys know what this kind of structure is called? It's a structural formula. It's also, this particular one would also be a Lewis dot structure. Have you done any Lewis dot structures? Little bit? Okay. We will be doing those later in the year. Okay. If you don't like them, that's okay. It's only because you haven't learned how to do them properly yet. Once you actually learn how to do them using a method, it's easy. Okay. They're hard when you're just trying to stick things together. The Bohr model, oh my God, the Bohr model will just like, oh, so many circles, so many dots. Okay. But this particular angle, I'm going to teach you this angle. This angle here is 109.5 degrees. Okay. And the thing is that if you had a flat structure, what would that angle be? That would be 90 degrees. Yes? What is that bond, that actual line, what's that actually made of? What's in that bond? Electrons. Okay, so the bond is made of electrons. So if you were to draw this actually showing the electrons rather than the lines, you would show it like this. You'd be like, okay, I've got a shared pair and a shared pair and a shared pair and a shared pair. Yay. Okay, there we go. That's also methane. That's another form of the Lewis dot structure. What do electrons do to other electrons? They repel one another. So they want to get up as far apart from one another as possible. So is that flat structure letting those electrons get as far from one another as possible? They are 90 degrees away from one another. Pardon me? Because they're on a flat plane. So if you allow that molecule, and nature does, if you allow it to become 3 dimensions, they can get further than 90 degrees. And the furthest you can get if you have 4 bonds, 4 sets of electrons, is this tripod structure, which we call a tetrahedron. Okay, it's a tetrahedron, and it has that bond angle of 109.5. Do you need to know this for this unit? No. Will you need to know it for a future unit? Yes. That's why I am mentioning it now. Yes. 109.5 is just as far apart as they can get. They can't get to 120 and still have 4 bonds. If you only had 3 bonds, there are certain molecules, like if you have F3, the farthest they can get apart, because there's only 3 bonds now, is 120 degrees, and that actually does form a flat molecule rather than a 3-dimensional molecule. Anything where you have 4 sets of electrons around it will always be that tripod, that tetrahedron. Anything with 3 sets of electrons around it will always be that 120 degrees. And this has got a funky name. This one is called trigonal planar, because it's a triangle on a plane. Trigonal planar. And that's 3 sets of electrons. So anything that has 3 sets of electrons is going to take that shape. Yeah? Anything that has 4 sets of electrons is going to form the tripod, but we don't call it a tripod. What do we call it? A tetrahedron, so the shape is called tetrahedral, okay? So this shape is called tetrahedral shape. That one was called, I'm sorry, I always write kind of funny. That is called a trigonal planar or trigonal planar. So trigonal planar is when you have 3 sets of electrons. Tetrahedral is when you have 4 sets of electrons coming off that central molecule. And why am I mentioning it now? Because usually when it comes at the end of the year, people are kind of like, oh yeah, the information comes out and then blah, it all goes out over the summer. And then you have to write the AP exam the next year and you don't remember it at all. Okay, so I'm just going to keep bringing these names up again and again as we go through the course, and they will start to stick, but you're not responsible for them until it appears on the front cover of a unit book. Yes? I will bring things up during the summer. I will bring them up over Christmas. You don't get rid of me for like, oh my God, the poor people who did AP chemistry last year because we were in semester 2, right? So, okay, we've got this entire grade 12 course to cover plus the AP stuff, and it's all done by May 2nd because that's when the exam is. So basically, they didn't get rid of me. I had summer stuff for them during semester 1 when they didn't have me. I'm like, okay, we're meeting every Tuesday, and here's an assignment. Okay, they learned 2 units essentially on their own, and then we did a blast through them. It was a terrible year. They did well. Most people wrote the exam, and the average score out of 4 was 3.66. We only had one person get no, we had 2 people get a 3 and everybody else got 4s and 5s. So, I mean, they were dedicated. Plus everyone who took it in 11, because it was such a weird year, we did hybrid quarter the year before that. Like we were the one that was in the afternoon and I only saw them every second day. So they did that in grade 11 and they had this weird thing in grade 12. I did have a fair number of people drop that year because they're like, this is too intense. I cannot, it was just too much. You learned half of it on your own and then you learned half of it on your too much. It was a bad year. This is better. And next year you guys will be first semester AP Chem. So we will learn it and then I'll send you little review things over second semester so you don't forget. Okay? Okie dokie. You'll never get rid of me. It's basically all chemistry all the time from the beginning of this summer until like you're done the exam. And when you're done the exam, I say goodbye. Too bad actually when it was a year-long course, when we hit May, we were just done and I said goodbye and you could come by if you wanted to and you didn't have to if you didn't want to. Yes? Yes.
Wait, why is it like that?
So, ladies and gentlemen, at some point I will have you build molecular models so you can actually see these, but this is sort of, I have a better one, but it's at home because they need a little bit of fixing and gluing right now. This one is kind of, sort of, somebody's old model, and it's not particularly symmetrical, but it should be perfectly symmetrical, whether you put it this way, or this way, or this way, it should all look like a little tripod. Okay. So I'll bring in my better one for you guys to take a look at. Okay, have you solved these problems while you've been waiting for me? Do you want to try them? You're going to want to have your unknown is equal to your initial times your conversion factor. Oh, and now this is all moved around. Oh my God. Okay, you guys try that. I'm going to fix this document here. Hi.
Is it supposed to be missing monohydrate? Like, honey.
Oh, yeah, that should have a monohydrate, yes.
Okay.
Yeah. Yeah, why is that not there? That's number 15.
Yeah.
Thank you.
Okay.
Yes.
So this question, I don't think this.
Oh, it doesn't match.
Yeah.
Okay, so that's what, number 29 and number
15.
15? Okay. 29. Did I do the first one correctly? 3A? You do not need to write any of this stuff. This is all just kind of like, yeah, it looks like cadum. And the O atoms look like otoms. Did I do it wrong? Oh. There we go. Does that look better? Because we've canceled out the CH4 molecules and now we have C atoms. Now, would you necessarily bother showing the work when it's a 1-to-1 ratio? You don't really have to. You could just say the number of C atoms is equal to the number of CH4 molecules is equal to 128. For a different situation, where you have a different number, then you would want to show the work. So we would have the number of H atoms How many sig figs should we have? How many sig figs in this number here, the 128? To be honest, it's a small enough number that it could possibly be counted. You might even say infinite because it could have been a counted number, okay? You're never going to get numbers that are ambiguous like this, okay? So don't fuss about that. Don't worry about that. That's never gonna happen on an AP exam, for example. But you could argue that that has infinite sig figs because it's a small enough number that you could have counted it, okay? But yeah, you would also be probably okay if you assumed that that had 3 sig figs. Now, how about that 4 H atoms per 1 CH4 molecule? How many sig figs here? Those are definitely counted numbers. Like we literally took a look at that molecule and counted 1, 2, 3, 4 hydrogen atoms. So those are exact. So how many sig figs? Infinite sig figs. Because it is counted. And same thing down here, infinite sig figs because it is counted. But like I said, for that 128, you could probably get away with either infinite or 3 and nobody's gonna get too excited, okay? For that one, because that conversion factor contains exact numbers, we don't worry about them. If it had contained numbers that had uncertainty to them, like 6.02 times 10 to the 23, then we would include that in our sig fig thinking. Yes, that's correct. Yeah, exactly. Would you like me to write up the answers to C and D up here? Yes, sorry, question, yes. Yes, if it is countable, it has an infinite number of sig figs. Like I said, on an AP exam, nobody's going to give you something that's ambiguous. You're either going to see a number like this, which is obviously counted, or you're going to see a number like now, if you have something like that, do you think that we have exactly that many particles, or do you think maybe it's a little bit more or maybe a little bit less? It's maybe a little bit more, maybe a little bit less. So if you see anything with like powers of 10, you can assume that those ones definitely have significant figures. So this would be 2 significant figures, okay? So are we feeling good about that? We are? Okay. Next page, 16. 5.1F. The only thing that's different here is that instead of having atoms and molecules, remember what kind of a compound did we have when we had a molecule? What kind of bonding? We had covalent bonding. Here we have maybe calcium, right, which is 2+, and phosphate, which is 3-. What kind of a compound is this? Yeah, it's made of ions. It is an ionic compound. The bond between the calcium and the phosphate is an ionic bond. Why does an ionic bond form? Like if I've got a Ca2+ and a PO4 3-, why do those things bond together? Why do they stick together? Let's make it even simpler. Let's say if I had an Na+ and a Cl-, why do those stick together? Yes. They have opposing charges. Opposite charges attract. So the attraction between opposite charges is what an ionic bond is. Yes. Mm-hmm. So within that polyatomic ion, the bonds between the P's and the O's, those are covalent bonds. So we have a compound that has a polyatomic ion where the atoms are bonded covalently, but then that entire thing has a -3 charge, and that sticks to the positively charged calciums. So it has ionic and covalent bonds within it. The bigger classification is that it is an ionic compound because it is made of ions, and the main structure is you have a cation and you have an anion. If you were to dissolve it, it would split up into the Ca2+ and the PO4 3-, but the PO4 3- would stay together, okay? So when we're looking at ionic compounds, we almost treat polyatomic ions as though they were a single entity, a single atom, even though they're not. But yes, absolutely, within a polyatomic ion, you have covalent bonds. So the phosphorus and the oxygen are sharing electrons, but then the whole thing has a negative charge, so it sticks to the positive calcium. Yeah? And like I said, again, there's a whole unit on bonding, so we will talk about that in more depth later, okay? For now, all you need to know is we have an ionic compound, and because we have an ionic compound, if you had another sodium atom floating around over here, what would it do? Would it keep hanging out over here? Everything's sort of bouncing around, la la la. Where would it end up eventually? It would be like Ooh, look at that lovely negative charge over there. And it would also form another ionic bond. Yes? And if we had another chloride ion floating around over here, I mean, they don't really float like this, okay? Just bear with me here. If it was magically floating around in the air like that, what would it do? It would go to the sodium and maybe it comes here. Oh, look, so there's a little bond there, and here now is our chloride. Yeah? And if I threw another sodium in the mix, where might it end up? It could end up down here, but I haven't left room down there. Okay, so I can't draw it there, but I could maybe draw it here. Yeah? And if there was another chloride, where could it end up? Maybe up in the corner, but again, I haven't left room for it. What structure would be formed? Yes, that is your ionic crystal lattice where you have it in 3 dimensions, okay? So you see they line up positive, negative, positive, negative, positive, negative. That's different from a molecule. A molecule does carbon dioxide ever have more than 2 oxygens? Nope, it's C, 1 C with 2 O's. Every carbon dioxide molecule is 1 C with 2 O's. If you had 2 C's with 4 O's, twice as many of each, you would have a completely different compound with different properties. But if you have a small crystal of NaCl, it will taste salty. If you have a large crystal of NaCl, it will taste salty. So in ionic compounds, you can have an indeterminate number of atoms. It just depends on how big the crystal is. Whereas in a molecule, you have a definite number of atoms. It's like set. So covalent bonding says, okay, we're done. You know, everybody's filled up their electron shells and we're done. Ionic bonding says, oh, more ions around, come join us, form a crystal lattice, form a bigger crystal lattice, okay? So that's really the only thing that's different here when we're talking about converting between particles, is it's just different kinds of particles. Have you heard the term formula unit? Not really, maybe, sort of. Okay, so we agreed that this right here, non-metals, is called a molecule, yes? And we agreed that if there are other ions floating around, we will never probably actually have a single sodium and a single chloride, right? Does it seem likely that there's only going to be 1 sodium and 1 chloride and they're like, okay, we're done now, and there's no more anywhere near? Does that seem likely? No, okay? So if there are other sodiums and chlorides, they will come and form this bigger structure. But it's still nice to be able to refer to a single unit of a single Na and a single Cl, just because it's a convenient way to refer to it. And so because it's not an official molecule, though, we call it a formula unit, okay? So a formula unit is like a molecule for an ionic compound, okay? So that is what a formula unit is. A formula unit, oh look, I wrote it here. Why am I writing it again? Okay, a formula unit, it is like a molecule for an ionic compound. Ionic compounds don't actually exist as molecules, groups of atoms with an exact composition like CO2, 1 carbon, 2 oxygens. And I'm sorry, you know what I realize I never make eye contact with people who are on the far side because it's like out of my peripheral vision. So hello over there and hello over there. I apologize. Like I make a lot of eye contact with the people like right in front here and sometimes in the back. Hello. Okay, so anyway, I will try and do better, but yeah. So they don't form molecules, they go on and on to form an ionic, what's the word? Crystal lattice. Okay. And this one alternates calcium phosphate, but you see it's a ratio of 3 to 2. There are 3 calciums for every 2 phosphates. Do I have another color highlighter? I do. How exciting, phosphate. What do you notice about the charges on the phosphate? Yeah, there's one for every O except for the one that is double bonded. Yeah, and we'll look more at that when we do the bonding and look at Lewis structures. So, how many calcium ions are in one formula unit of calcium phosphate? So this is a picture of that, which is the formula unit. It's not as pretty a picture as a molecule, is it? But it's still seeable. We still have how many calciums? We still have 3 calciums, so there are 3 Ca2+. Anytime you write an ion, you must write its charge.
The assembly will start promptly at 8:35 and it will end at 9:25. This is for the grade 9 students only, and please go to the large queue tomorrow morning at 8:35. Thank you.
Do you think that using what you know about molecules and atoms, you could translate that into using conversion factors with formula units and ions? Do you think you could attempt this on your own and we could check it over next day? Yes? Okay, so your homework is to attempt 5.1F, which is just pages 16 and 17. And because we got to keep moving, we got to move super fast. I'm going to have you hang out with Tyler for a little bit, 5.2A. Okay, so do your best on 16 and 17. We will go over it next day and then hang out with Tyler for 5.2A. Yes? No, we're just doing 5.2A. Just A. 34 to 36. Yes? So fast and so nasty. You want to do whatever you want. Like anything you can do. Well, we'll actually, maybe tomorrow we'll read for a moment, just talk about space and class, and yeah, absolutely. Yes, do 5.1C as well. It's a good idea. It'll allow us to move a little bit faster next day. So if you missed that, everyone's mad at Daniel now, but it was a really good idea that we do 5.1C also. Somebody did 5.1C. How long did it take you to do 5.1C? 15, 30 minutes? If you do like only half of it, that's fine, right? Like if you're like, okay, I can only fit in half of this, just do like every other question. Okay, this course does move super fast. There is a lot of work. So if you're finding that you can only do half of something and you're going to leave the rest of it for a little review, that is okay. You're going to need to do what you need to make life work for you. And we'll talk a little bit more about that next day also, because we need to talk about how to make this crazy world where we teach 3 years of material in 2 years to people who are 2 years younger than everyone else who's doing it.
I have a quick question about the lattices.
Yes.
So, as I understand it, when Na and Cl come together,
Yeah.
they share one of the A's electrons. Cl uses that one.
Yes.
Together, are they not balanced? So
Yes.
why would another Na want to join balance?
Okay, so what's going to happen is that you're going to have a chunk of sodium and then some chlorine gas floating around. All of the sodiums want to give away their electrons, and all of the chlorines want to grab an electron. So what's going to happen is all the sodiums are going to be grabbing electrons as fast as they can from the chlorines, and all the chlorines are going to be taking them, and now you have a pile of sodium ions and chloride ions, which are going to arrange themselves, tick, 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 positive, negative, positive, negative.
They're sharing all these charges.
So they're transfer electrons. It's the stablest way of being
It's like you
organized.
could do hexagons. That would be like super practical and would collapse in itself.
So there are actually crystals that are hexagonal. It just depends on the ratio of atoms. So we usually use something really easy to draw where it's a 1-to-1, because you see what it looks like when we've got a 3-to-2 ratio. I didn't even try and draw a crystal lattice for that because it's really hard. You can look up pictures of them. They've got lines going like this and like this. You know, like it's crazy. Yeah. So basically, yeah, that's what it is. They end up, they try to go to the most stable arrangement possible. So the most stable is where you have alternating positives and negatives. Hi. Let me move this out of the way here. Yeah.
I assume you only write the charges for atoms.
Only if it's an ion. So here, it's an ion, right? Because it's part of an ionic compound.
Would you ever do it for?
You would never do it for covalent compounds. Okay, so these ones are atoms. These ones in the ionic compound are. So you would do PO4 3-, yes. Okay.
So
yeah.
it's only for ionic.
Only for ionic. Yeah.
Compounds and they're separate atoms.
Yeah, and when you write the compound together, you don't write a charge because they cancel each other out. That's right. That's right. Hi.
I was just wondering for this,
Yeah.
is this correct? Because in the answer key, I think it's 5.15 times 10 to the power 21.
Oh, maybe I typed it wrong.
Just this one right here.
Okay, I'll check one.
Because I was just trying to do it.
Yeah.
No matter how I did it,
It always
decimal
ended
never
up.
moved.
Okay.
So, like I was just rounding it, right, for significance.
You know what? Honestly, that looks much better. Yes. No, you've got to be correct because 3 and 23 is going to give you closer to 27 and 21.
Okay.
So I must have typed it wrong.
Okay.
Yeah.
Thank you.
Hi. Yeah.
The pages, are those also the pink books?
So yeah, they're all in the pink book. Everything's in the pink book.
My homework is usually always.
Oh yeah, unless I tell you otherwise.
Okay.
Yeah.